So we're given this physics problem, which is actually an interesting problem because it involves some chemistry in it. It's asking us if a point charge with the same charge and mass as all the sodium ions in a zero point 0.1 mole of sodium chloride is 2 centimeters from a point charge with the same charge and mass as all the chlorine ions, what is the magnitude of the attractive force between these 2 point charges? And so you'll know from chemistry that 1 mole is equal to 6.022 times 10 to the 23rd atoms or molecules, atomic particles, which hopefully we know as Avogadro's number. We'll abbreviate it as AV, Avogadro's number. And so the question is asking us, imagine that the point charge is basically 0.1 times Avogadro's number amount of Na plus ions, and the other point charge being 0.1 times Avogadro's numbers of chlorine ions. So since one is positive and one is negative, we're going to have an attractive force between them. And of course we know by Coulomb's law, part A, by Coulomb's law we know that the force between those two charges, the magnitude, is going to be equal to some constant k, or 1 divided by 4 pi epsilon 0, times the magnitude of the first point charge times the magnitude of the second point charge, all divided by the distance between them squared. So for the first point charge, Q and A we'll call it, is going to be equal to 0.1 times Avogadro's number times Avogadro's number. That gives us the amount of particles that we have, and since we know each particle has a charge of a positive charge, we can multiply this whole term by the magnitude of a charge, which we know as, or you can look in the back of your book or online, as 1.602 times 10 to the negative 19. And that will give you the charge of 0.1 moles, or 0.1 times Avogadro's numbers charge. And that will be the same, actually, because these are both magnitudes. QCl minus will be equal to the magnitude of Q and A plus, because we're dealing with the same amount of particles and it's going to have the same exact magnitude of the charge. And so if you do 0.1 times 6.022 times 10 to the 23rd multiplied by 1.602 times 10 to the negative 19, you should come up with 9,647.244 coulombs. That's a massive charge. And so to answer the question now, finally, we know that we know Q. Since we know they're both going to be the same amount of charge, we can write this as K, which we know is 8.99 times 10 to the 9th, multiplied by 9647.244, we'll just call it Q, squared, because they're both the same exact magnitude of charge, divided by r squared. What was the distance they said? They said that they're both a distance of 2 centimeters away. But of course we can't keep it in centimeters because we use SI units, standard international units, which will have to be in meters. And so 2 centimeters is equivalent to 0.02 meters squared. And in the end you should come up with 2.09 times 10 to the 21st newtons. And that is also a massive force. And remember, the reason this force is so massive is because we're talking about zero point 0.1 times 6.022 times 10 to the 23rd charged atoms. So we're not talking about one single atom, we're talking about many, many atoms that are all charged, and we're talking about them as 1 point charge. So that's why the force is so massive. And so point B is basically a problem that we can use from basically first semester physics. It says if the positive point charge in part A is held in place and the negative point charge is released from rest, what is its initial acceleration? So basically what he's asking us is, imagine we took the positive point charge, the Na1, we held it in place. Make believe that's some sort of a claw holding him in place. And we have this negative ions, this is a Cl1, and he's going to be going this way towards him with the same force that we found above in the first part, with an acceleration that we're not sure of. From first semester physics, we know that F is equal to ma. So we need to figure out this mass. In order to do that, we can use some chemistry that we know. We know that by looking at the periodic table, that the mass of one chlorine atom is equal to 35.45 grams per mole. And if we multiply that by the given amount that we were given, because we weren't given 1 mole, we were given 0.1 mole. And of course, since he's in grams, he has to be in kilograms. We might as well multiply this by 10 to the negative 3 for a standard conversion. That'll be kilograms per 1 gram. You'll see that the moles will cancel and that the grams will cancel, and that we will be left with 35.45 times 10 to the negative 4 kilograms, which is just what we need for that mass amount, and we have the force and we have the mass. So acceleration will be the force that we found up here, that very large one, 2.09 times 10 to the 21, divided by the mass amount that we have here. And if you do the math on a calculator, you'll see that we'll come up with 5.9 times 10 to the 23rd meters per second squared, which is extremely fast. And for part C, they're asking us, does it seem reasonable that the ions in sodium chloride could be separated in this way? Why or why not? So it's kind of a trivial question, actually. If you go onto Wikipedia and you look up how much force is required behind taking the space shuttle to space, you'll see that that's equal to 12.5 times 10 to the 6 newtons of thrust. That was the thrust produced by the space shuttle engines. The force here is 2.09 times 10 to the 21 newtons. Ours is just 10 to the 6th, so I would say that it's not even close, and that the answer for that question is a clear no.